So at the very high level, what I want to talk today is about the allocation of scarce resources in socially sensitive settings, and in particular about issues of fairness, efficiency, and transparency. A few words about the Center for AI in Society. We are an interdisciplinary research center between the Schools of Engineering and Social Work at USC. So we conduct research in AI with aim to address important societal problems. And we're very much interdisciplinary in the sense that most of our projects involve collaboration between peoples from engineering, computer science, and then social work. Here you go. So a little bit about an overview of my approach, so you can situate yourself, since I'm quite probably different from in background from the others. So I try in my research to take an end-to-end approach, in the sense that most of my projects start from collaboration with a community partner or policymaker, asking them what are the problems that keep them up at night. I myself, I'm an optimizer. More often than not, the problems they face are decision-making problems. So I'm going to frame the problem they're faced with as a mathematical optimization problem, where we're trying to maximize some objective subject to hard constraints. And most of the problems I'm faced with actually involve uncertainty, in the sense that we have to make decisions in, taking into account the fact that there's things that we don't know how they will materialize in the future. These problems are usually very hard to solve, and my research group is focused on developing solution approaches for addressing these hard problems. So we're very much on the computation side, but at the same time, we're looking to deploy our solutions. And so that's where issues of fairness and so on come in particular, as we're working in the context of socially important, socially sensitive problems. Throughout the project, we involve our partners to ensure that we're actually solving the problem that they're interested in. So I said I'm going to talk about resource allocation systems. What do I mean here? So a resource allocation system is basically an automatic system that's going to allocate automatically scarce resources of different types to heterogeneous individuals, like allocatees, that need them. Many resource allocation systems operate in settings that are socially sensitive, in the sense that they are concerned with the allocation of resources that are needed to satisfy one's basic needs. So shelter, food, education, sanitation, and so on. And oftentimes these resource allocation systems, the way they operate is that they generate a rank ordered list of individuals to help basically with prioritization decisions. So some examples are the housing allocation system, whereby we have housing resources of different types, so permanent supportive housing, rapid rehousing, and then we want to allocate these resources of different types to individuals experiencing homelessness. These individuals have different characteristics, and they will benefit in different ways if allocated any given resource. Another example is the kidney allocation system, whereby deceased donor kidneys of different quality, all they are, etc. And these kidneys of different types, we seek to allocate them to patients that themselves have different characteristics and that suffer from end-stage renal disease. So it's for them a question of life and death, basically, of receiving that organ or not. So at the high level, what I've said so far is I've motivated the need for automated resource allocation systems that allocate resources of different types to individuals that have different characteristics. Examples I gave were the kidney allocation system, where we allocate deceased donor kidneys to patients suffering from end-stage renal disease, the housing allocation system, where we allocate housing resources of different types to individuals experiencing homelessness, and finally, the current healthcare system, where we need to prioritize individuals suffering from COVID-19 for critical healthcare resources. naturally, when we're allocating basically resources that are needed to satisfy one's basic needs, and that are very scarce, this raises a huge number of ethical dilemmas, for example, related to the trade-offs between fairness, efficiency, and interpretability. Indeed, if I'm trying to design a system that is extremely fair, for example, over the protected characteristics of individuals, then naturally it's going to be less efficient, potentially also less interpretable. On the other hand, if I try to make it more efficient, then presumably I'm going to have to sacrifice fairness. The reason being that we are operating in a regime where there's very scarce resources, and so some people will not get access to resources, unfortunately. And this has been documented a lot in the press in recent days, starting with Italy, where we've seen that doctors have actually had to make very hard decisions in terms of who they will be prioritizing for care. And it's been reported that actually younger patients have been prioritized. And this has raised in the US a number of strategies. It has motivated a number of strategies for creating discipline strategies or systems, rank-ordered scoring systems for prioritizing individuals for care. So beyond those ethical dilemmas, there's also more complications. First of all, that in most of these resource allocation systems, we have various stakeholders that are involved. For example, doctors, patients, the government, the population at large. And at the same time, these are systems where typically there is a lot of uncertainty about the arrival time of the resources, about the arrival time of patients, the types of patients that will arrive. These systems are typically unstable and non-stationary in the sense that the demand may change over time, and it's also highly unpredictable, making it very hard basically to make good judgment calls. And so for these reasons, basically the ethical dilemmas, uncertainty, and stakeholder multiplicity, we need a disciplined and automated way to allocate skills. And so this raises a number of questions in AI. The first one is how can we elicit, encode, and aggregate the conflicting preferences of stakeholders so as to be able to design the system in a way that's going to meet their needs. Second, how can we model uncertainty in a way that's going to capture the unstable and non-stationary nature of the system, and how can we look at abilities? So let's say I'm trying to optimize efficiency. How do I know, how can I estimate the probability that I'm going to have a successful outcome if I match a particular resource to a particular individual? And finally, how can I design an allocation rule that's going to align with stakeholder preferences in terms of fairness, efficiency, and transparency, and that takes into account the dynamic nature of the process and any fairness considerations and more generally, right, the preferences of stakeholders in terms of these three aspects. How is the sound? Is it okay so far?
Great.
Thank you. All right. So for my talk, I'm going to focus on the housing allocation problem. And in particular, the reason why I chose to focus on this problem is because we have a concrete partnership with the Los Angeles Homeless Services Authority, which is the entity that's in charge of allocating scarce housing resources to those experiencing homelessness in all of LA County. This is in collaboration with with Eric Rice, who is a director of the Center for AI in Society. And on the picture, you can see me, Eric, and various policymakers discussing the issues I mentioned. So the motivation for our work is the homelessness crisis in LA and generally in the US. In LA, the numbers are actually staggering. Sorry, this is actually outdated a little bit. The current number of homeless individuals in LA is in the order of 58 are unsheltered. And unfortunately, the total amount, And so we are indeed in one of those settings where we have far fewer resources, in fact, than we have individuals that need them. So what we propose in this work is to create a data-driven system for prioritizing individuals for these scarce resources. We've identified that there's basically three main building blocks to be able to solve this problem. The first one, which relates also to a point I made earlier, is to understand what it is that policymakers, and I should say here, in fact, broadly speaking, stakeholders, what it is that they're looking for in terms of this system. So we need a preference elicitation module that will be able to quantify and compare different choices of policy in terms of their outcomes and in terms of their characteristics. The second part that we need is a machine learning module, which, using historical data, can help predict how one will do if matched to a particular housing resource. This is to be able to evaluate the performance of other policies that we would choose. And finally, we have a policy design module that should combine these two inputs to generate policies that are going to meet the needs of the policymakers. Our goal ultimately is to evaluate policies designed by this system in the real world and to ensure they meet the needs of the various stakeholders involved. So let me talk about these steps, and again, so comments are more than welcome. So the first step is this preference elicitation and aggregation step. So let me tell you a little bit about the current system for allocating housing resources in LA so that you can understand what our starting point is. So the current policy is based on a scoring rule that's called the VISP-DAT, also referred to as a vulnerability score. Each time an individual comes into the system, they are assessed so that we can assign them a score. This assessment consists in asking them a series of questions, and depending on how the question is asked, they get a particular score. All the scores are added up together, giving them their VISP-DAT. Based on overall vulnerability score, the vulnerable lie in the immediate service zone. Basically, you get housing resource forever provided you comply with the rules of the resource. Rapid rehousing is a short-term 3-month voucher-based intervention, so quite a bit less supportive, I would say. And then with services only, you do not get any housing resource. One potential drawback of this system is that it's not tied to outcomes, so that what resource you get is not necessarily linked to how likely you are to succeed in that resource. And there's no explicit, perhaps, fairness considerations. All right, so in our first meeting with LASA, we sat down and discussed with them what it is that they would policy to achieve. And really they mentioned 3 desiderata. The first one is policy to be fair. The second one is they would like it to be efficient. And the third one is that they would like it to be interpretable. So let's dig in a little bit deeper. Here, one challenge, of course, is that fairness is extremely broad. It's very hard to define what fairness means. Are we talking about fairness in opportunity or fairness in outcome? Are we talking about fairness, racial fairness, fairness by gender, and so on? We need to define this notion somehow. Then what about efficiency? Again, in homelessness, people are going to follow very complex trajectories in and out of homelessness. So to evaluate what is a good outcome is actually itself very hard. And similarly, interpretability, intuitively, we want to have a way to explain why a particular individual was given a resource rather than someone else. However, what I deem to be interpretable may be completely different than what someone else may deem interpretable. And so what we would like, again, is to have a way to understand how what stakeholders mean by these things, and also what they would prefer. So if I give you something that's more interpretable and slightly less fair, would that be okay? And in fact, they mentioned to us that, quantifying how people are thinking about these trade-offs is one of the burning issues for them at LASA. So one standard way of understanding preferences in probably in marketing, in economics, and in AI generally as well, is to ask people pairwise comparisons. So say I want to understand your preferences in terms of fairness and efficiency. I have here a very crude and simplistic example to illustrate my point. I could ask you I could show you the outcomes of some policy A on the left on the screen, and then the outcomes of some policy B on the right on the screen. So policy A, if we look at it, it's a kind of not unfair, not fair in terms of its outcomes. So white individuals are a lot more likely to succeed, whereas on the other hand, it is quite efficient. So overall, an individual picked at random in the population is quite likely to be able to exit homelessness. On the other hand, policy on the right is extremely fair, but it is less efficient relative to policy A. And so by asking if you prefer policy A or B, now I can get an understanding of how much you value fairness and versus efficiency. And so by asking a series of questions of this type that perhaps complement one another, I can get an understanding of your preferences. Naturally, there are a lot more dimensions to this problem, a lot more dimensions of fairness, a lot more dimensions of efficiency. This is purely for illustration purposes. Are there any questions at this point? All right. Is the sound okay? I'm going to assume that it's okay, so long as I don't hear something.
It's working well.
Thank you, John. All right, so now, of course, the difficult question becomes at this point, which question I should be asking, right? And which series of questions I should be asking. This is very complicated because there's a myriad policies that I could be comparing to one another. And stakeholders typically have very limited time to actually answer these questions. They cannot spend like 10 years trying to answer these questions. And so the question, then the algorithmic questions that comes that comes up is which questions should we be asking to gain the most useful information? So in our paper, we investigate two elicitation strategies. The first one is motivated by the setting in which we operate, where we are also interested in going on the streets and interviewing individuals experiencing homelessness. This means that we cannot have access to a computer that can adaptively come up with queries for us. Instead, we need to select from the onset which pairs of questions we're going to ask. Then we go out on the field, we ask the questions, we observe the answers to those questions, and then using the information that we gain, are able to then design a policy that is going to best meet their needs. And so what we propose in our work is an algorithm that's going to integrate the elicitation and the recommendation phases. This is somewhat different relative to the existing literature, in the sense that most of the literature seeks to maximize information gain in some mathematical sense. We explicitly try to gather information that's going to be useful for the downstream recommendation problem, which may be different than the questions that you would ask if you were just looking to maximize information. So in other words, our questions are going to change depending on the set of possibilities that I have in the second stage, my recourse actions. We also investigate an adaptive elicitation setting, which adaptively selects questions received. Again, our algorithm is going to integrate here the elicitation and the recommendation phases. Naturally, adaptive elicitation is preferred because if I'm able to adjust the questions I asked in response to the answers I get, then I can basically make more strategic, be better. But in some settings, it may not be practically feasible to go with this adaptive elicitation approach. So I'm just going to show you some results here, and I welcome any feedback regarding interpretability of the results. So to give you a bit of an idea, here what we did is we considered different sets of candidate policies that had different characteristics. So this is both a computational experiment, but also a bit of an experiment of trying to understand how good are the recommendations that we can actually make to the user. So here we're trying to recommend the item or the policy that it's going to be the best in the worst case. It's going to maximize the worst case utility. Though we're taking the worst case here because we do not really know the utility of the user. We just get some information as a byproduct of the questions, and then we can evaluate the worst case utility based on the information we gained. So in the first row, we are increasing the number of policies that we can choose from to ask questions. In the second row, we're increasing the number of features. Intuitively, the higher the number of features, the more complicated the problem is going to be. And in the bottom row, we are increasing uncertainty in the sense that as we increase uncertainty, we're not going to trust so much what the user is going to tell us. We're going to take it with a pinch of salt. On the y-axis, we're showing the worst case utility. 0 would be the case where you don't ask any questions, so this would be your starting point. And then 1 is the case, the best possible case, where you have asked all the questions. So as you can see, as we increase the number of questions that we ask, sorry, I should have said something more. The red is our approach and the blue is random elicitation. So this would say, what if I pick questions to ask at random, ask them, see your answer, and then recommend an item. See your answers and then recommend an item. So the blue, because there's several choices of questions that I could draw at random, here we have drawn 100 possible choices at random and we're evaluating their performance. As you can see, our approach consistently outperforms that approach. As we increase the number of questions, our approach performs better and better. And in fact, even with just one question, we're typically able to cover most of the gap as if we had asked all of the questions. I'm going to skip this slide, which is more computational. At the high level, what it shows is that the time needed to evaluate the quality of a random query is too slow, and you wouldn't be able to evaluate all random queries. It's better to optimize directly on the set of queries to ask. These results are for the online elicitation problem, where I can adapt my questions in response to the answers I received. Our approach is again the red approach. The blue approach is random elicitation, and here we are showing the median performance of all approaches. And then the green approaches are some algorithms developed in the literature. As we can see, other approaches are comparable to random, whereas our approach typically after 5-6 questions is able to make recommendations that are as good as if basically you had you had asked all of the possible questions. This is, of course, not the case if we don't really trust the answers of the user, then we become more limited in our ability to gain useful information. In terms of the rank of the recommended item, you can see that our approach not only offers items that are a lot better in terms of worst case utility, but are also better in terms of the worst case rank of the item that they offer. We performed some experiments on real data as well, where we're trying to minimize regret. So the idea here is we took historical data from the homeless management information system across the US, and we used that data to simulate the performance of various policies. And then we used these policies as a way to, as a possible set of policies to ask questions from. And then we tried to select questions in a way that's going to minimize regret. In the regret case, what you want to do is to have as low regret as possible. Intuitively, regret measures how bad you feel in hindsight. If you were to know the truth about the preferences, how bad would you feel? So the closest to zero, the least bad you feel, the least regret you feel. And so again, we outperform random elicitation significantly. This is for the offline elicitation or for the static elicitation. In the online elicitation setting, again, we outperform by recommending or regret. This is even more true on this real data set where most other approaches remain worse than one. So this algorithm only works in the presence of a single stakeholder. What we are working on right now is to generalize this algorithm so it can work with multiple stakeholders, whereby we select not only what questions we're going to ask, but also whom we're going to ask them to. And then we're looking at notions of fairness in terms of the item you recommend and in terms of how unhappy you make the various stakeholders. We have a user interface that we are working to deploy in the real world. We're a bit slowed down, I guess, by the pandemic. But this interface, what it does is it shows candidate policies, policy A and policy B, and displays their differences in terms of what kind of policy they are they a scoring rule, are they also in terms of their outcomes? So what is your success by gender, your success by race, success overall, and so on. So this is system level outcomes of the policy, where this is connected with our algorithm and questions are chosen adaptively to learn the information from the stakeholders. Any questions at this point? How much time do I have left?
I think, yeah, we have, according to the original plan, 7 minutes left in this slot. So I think
that's perfect.
Yeah, if there are questions, it might also be good to keep them for the end.
So this brings me to the policy design part. Now, having learned the preferences of the stakeholders, what you would like to do is to design a policy that's going to meet their needs. So we take the point of view that the system we are seeing is what is called in operations research a queuing system. So you have individuals that are queuing up for resources. They are individuals of different types, and then you have servers which correspond. And what we want to do is to design a policy that's going to use the features of the housing resource and the features of the youth or the homeless individuals. In this case, we were looking at the homeless youth population in the US to basically score-based policies that are going to prioritize the waitlisted homeless individuals for this housing resource. We focus on what we deem to be our interpretable policies, which are either linear scoring rules, just like the one that is currently used in LA, or decision tree based policies where all in a different leaf and get assigned which features we're going to be branching on, and then how many points will be allocated to each individual based on this, on which leaf they ended up on. Yes, the motivation for using such policies is that most policies that are currently in use actually take this form. This is true in the kidney allocation system and in the housing allocation system. I believe it's starting to be true for the systems that are used in hospitals to prioritize patients. Naturally, as I mentioned earlier, we're looking for our policies to be fair. So right now we have not yet connected the preference elicitation part with this part. However, it is doable. I just don't have results on it yet. So here we considered various settings and different preferences of individuals in terms of fairness. We assume that the stakeholders are interested in maximizing system efficiency subject to fairness constraints. So in our numerical results, we looked at fairness in terms of racial outcomes, gender outcomes, and vulnerability scores. Our framework works even if we were to incorporate other or more general criteria or different criteria. One key difference relative to using classical machine learning is that here we are explicitly taking into account the dynamics of the system, the fact that individuals and resources both arrive over time, and the fact that only so many resources are going to arrive in any given time period, so that strategic decision making is basically needed. What we find is the following. So this figure shows kind of in the evaluation phase how our proposed algorithm would work if what we want to achieve is maximize efficiency subject to fairness constraints. On the left-hand side, we see the performance of various policies, and on the y-axis, on the x-axis, we see on the left the probability of success across all homeless youth, and then the probability of success by race. As we can see, our approach, which is here at the bottom, with different kinds of structures of policies, decision tree-based policies with different depths, and then linear policies, outperform the benchmarks. So what are the benchmarks? TIE is the current allocation policy for homeless youth. Random is you prioritize on a first come, first serve basis, and these are machine learning based policies. So we outperform in terms of efficiency because we effectively take into account both the dynamics and the resource limitations. And on the other hand, we also outperform in terms of fairness, in particular looking at this last policy here, as we see that the success probability by, in terms of outcomes by race are more even. And again, this is not to say that this is what everyone would want in this system. This is just that when this is what we seek to impose as a measure of fairness, our algorithm basically achieves that. So we're able to mitigate 72% of racial bias and to increase efficiency by 16%. Now, there's a few limitations in this system. As I mentioned, this is preliminary work. So things that we are working to improve right now is the following. So the first thing is that we're not really taking into account uncertainty in the arrival times of individuals and resources. We're taking the point of view that the system is going to be stable in the sense that we're training it on historical data, and we're saying that the arrival times are going to be similar for the future. We then evaluate on new unseen data. However, I imagine, so it worked quite well on this unseen data, but I do imagine that if the system is unstable and non-stationary, there would exist better policies than the ones we are designing now. The other thing is that the way in which we are to predict how someone will do if placed in a particular resource is critical in trying to evaluate how fair a policy is or not. And so this means that somehow the prediction problem and the problem of designing the policy are closely interlinked. And so we need more, we need to be thoughtful somehow in how we're going to be predicting outcomes. In our framework, and so we're looking at ways to improve that right now. So this was my last step, this work. My students are on or computer science. So right now I have a visiting student, Simon from the School of Philosophy, who's working with me, and Caroline on the, also collaborated with many cases and for these ideas. So my presentation is based on a few papers. Some of them are under review, others accepted. Thank you so much.